Hi, I'm Joshita and I'm here to present our work, a hierarchical coding scheme for glasses-free 3D displays based on a scalable hybrid layered representation of real-world light fields. Current generation autostereoscopic display techniques are seen as an alternative to stereoscopic 3D as they support both stereopsis and motion parallax. Emerging multi-layered light field displays are a kind of glasses-free or autostereoscopic displays that provide continuous motion parallax, greater depth of field, and wider field of view. The given figure shows a schematic of a multi-layered light field display that has light attenuating layers stacked in front of a backlight. Here, light rays can pass through different combinations of pixels in the stacked layers depending on the viewing direction. Hence, the light field can be reproduced using this configuration of a computational light field display. Now, deploying actual light fields for display applications will require adequate representation and coding solutions. But existing light field coding algorithms are not generalized to adapt to a variety of autostereoscopic displays, including multi-view computational light field displays. In this paper, we propose a novel hierarchical coding scheme for light fields based on a hybrid multiplicative layers and Fourier disparity layers representation. The input light field is divided into two subsets based on the circular 2 or the hierarchical 2 scanning order as given in the figures. We derive the optimal multiplicative layers of each light field subset and exploit the redundancies among them by obtaining the hidden low-rank structure in the Krylov subspace. Encoding of these approximated layers using HEVC or the high-efficiency video coding further eliminates intra-view and inter-view redundancies. Next, the entire approximated light field is processed in the Fourier domain. A Fourier disparity layer or the FDL calibration estimates disparity values and angular coordinates of each light field view. This helps in the FDL construction and view prediction. We now split the approximated light field into subsets as identified by the circular 2 or the hierarchical 2 pattern. The first set of views is encoded and used in the construction of the FDL representation. This FDL representation is then used to synthesize the second subset. The set of views which are obtained from decoding the residual are again employed to refine the FDL representation and predict the next subset of views with improved accuracy. This hierarchical procedure continues iterating until all the light field views are coded. Thus, our scheme works in both the spatial domain and the Fourier domain in a hybrid manner to effectively exploit the intra-view, inter-view, and other nonlinear correlations present in the light field structure. Here is the complete workflow of the proposed scheme. Component 1 depicts the block in which the light field is divided into two subsets based on the circular 2 or hierarchical 2 pattern. The optimized multiplicative layers for each subset are obtained from CNNs, and this is followed by their low-rank approximation and compression. In component 2, the input is the approximated light field, and we will be working in the Fourier domain. The first subset is used to construct the FTL representation, which then aids in the synthesis of views of the second subset. There is an iterative refinement of the FTL representation here in component 2, and this is done till all the approximated light field views are encoded. Our decoding scheme is depicted in component 3. The angular coordinates and disparity values of the low-rank approximated light field, along with the encoded bit streams of the approximated subsets 1 and 2, are utilized for the final reconstruction of the entire light field. Here, we have shown the expansion of component 1 into 3 further blocks. As stated before, this component performs the low rank approximation of the different subsets of the input light field. Here, block 1 represents a convolutional neural network that converts the light field views of the input subsets into 3 optimal multiplicative layers. In block 2, the intrinsic redundancy which is present in the subset views is removed by exploiting the hidden low rank structure of the multiplicative layers, and this is done on the Krylov subspace for various ranks. HEVC encoding of these low-rank approximated. In block 3 of this component 1, the approximated views of the subset are reconstructed from the decoded layers, and the entire approximated light field is obtained at the end of component 1, which is then moved on to component 2 for further compression through the FTL representation as previously mentioned. The performance of the proposed compression scheme was evaluated on real light fields captured by Plinoptic cameras. We experimented with 3 data sets: bikes, fountain and Vincent 2, and the stone pillars outside. These are light field datasets from the EPFL light field JPEG Plano database. The circular 2 and hierarchical 2 coding patterns were constructed from the inner 9x9 light field views for all our tests. Here, the 9x9 bikes light field is shown along with its subsets for each of the pattern. We compared our coding scheme with the direct compression of light fields using FTL proposed by Elin, Dib and group. The bitrate versus PSNR graphs for the bikes data is shown here. Evidently, the proposed coding scheme outperforms the anchor by large margins. The same trend in ray distortion curves is observed for the fountain and Vincent 2 and the stone pillars outside light field datasets. The total number of bytes taken by our approach is comparatively far lesser than the work by Elin, Dib and team for all ranks and quantization parameters. These corresponding results are highlighted here in Table 1 for Circular 2 pattern and in Table 2 for the Hierarchical 2 pattern. Further, we use the Jean-Tegard metric to analyze bitrate reduction of our scheme with respect to the scheme by Elin, Dib and team. The average percentage difference in rate change was estimated over a range of quantization parameters for the 7 chosen ranks. A comparison of the percentage of bitrate savings of our proposed coding scheme with respect to the anchor method for the 3 chosen light field datasets is shown here in Table 3. For the Circular 2 pattern, the proposed scheme achieves about 94%, 96% and 93% bitrate reduction compared to the anchor for the light fields bikes, stone and fountain respectively. For the Hierarchical 2 pattern, our scheme achieves about 97% bitrate reduction for bikes, 97.5% for stone, and 96.5% for the fountain over the anchor scheme. The critical advantage of our proposed hybrid layered representation and coding scheme is that it utilizes not just spatial and temporal redundancies of the light field views, but it also efficiently exploits the strong intrinsic similarities which are present in the neighboring sub-aperture images in both horizontal and vertical directions as specified per the 2 prediction orders. Our scheme offers flexibility to cover a range of multiple bit rates using a single integrated system. This feature sets our work apart from other existing light field coding methods, which usually train many systems or networks to support only specific bit rates during the compression. Besides, existing coding approaches are not explicitly designed to target layered light field displays. Our coding model can also complement existing light field displays and is adaptable for a mobile, head-mounted, tabletop or other autostereoscopic display types. The compression performance analyzed with real light fields shows substantial bitrate savings and it maintains good reconstruction quality at the same time. That concludes the presentation. Thank you.